Hello everyone, I hope that you all are doing well. Today we discuss a very interesting concept which is known as diagonal argument or the diagonal process. This argument is mainly used in the analysis of PDE. In the analysis of PDE, we mainly create a sequence of solution and shows that this sequence of solution has a subsequence and the limit function of that subsequence is our required solution. This is the concept. Okay, but here the main problem is that when we generate a sequence of approximate solution, it is suppose that it is given on the unbounded domain 0 to infinite. Okay, but when we apply some compactness theorem like Arzelà-Ascoli theorem, Hellis theorem or Rayleigh-Kondrashov theorem, these theorems has some limitation. These theorems have some limitation means then that these theorems are only applied on the bounded domain 0 to t closed interval or bounded or compact domain 0 to t closed interval. But we need our limit function should be on the 0 to infinite unbounded domain. This is the main problem. Here the main role of the diagonal argument comes. Okay, suppose in our analysis we are allowed to apply this Arzelà-Ascoli theorem or Hellis theorem or Rayleigh-Kondrashov theorem on this 0 to t closed interval but for every t. Okay, then how can we ensure that our limit function is also on the 0 to infinite instead of 0 to capital T? Okay, that is our main target. Okay, so when we apply the compactness theorem, we extract a subsequence this and a limit function this. Limit function this such that it converges to this function pointwise sense. Okay, but here most of the times we forgot to write that it belongs to t belongs to 0 to t, but we do not, most of the time we do not care about this. We write it t belongs to 0 to infinite, but this is not a major mistake. But when we write this thing but we use a word, it is called the diagonal argument or diagonal process. Okay, if you are not using this word then you are making some mistake. Sometimes reviewer ask about that. Okay, so the explanation to write this t belongs to 0 to infinite is given here. Okay, we know that for every t we can apply this theorem, Arzelà-Ascoli theorem or Rayleigh-Kondrashov theorem or any type of compactness argument. So for when we apply the Arzelà-Ascoli theorem or the compactness theorem for t equal to 1, we extract this convergent subsequence, this one. Okay, so the limit function of the subsequence, suppose it is f1 tilde, so it is defined on where? It is defined on 0 1 closed interval. Okay, similarly when we take t equal to 2, we apply the same compactness theorem but on the subsequence this one. Okay, not the initial sequence fnt. We apply this when we take t equal to 2, we apply the compactness theorem on this extracted subsequence. Okay, then we extract this subsequence, second subsequence, means this second subsequence is the subsequence of the first one. Okay, then we get a limit function. What it gives? The limit function f2 tilde, and f2 tilde is defined on 0 to t closed interval. Here can you tell me that what is the relation between f1 tilde and f2 tilde? Certainly f1 tilde and f2 tilde are same on 0 1. Okay, why? Because both are the convergent sequence and the second one is the subsequence of the first one. Okay, and both are convergent, and we know that convergent sequence converge to the same limit, therefore f1 tilde and f2 tilde should be same. So if we proceed like this, then we can generate these type of sequences, but every time the former limit function and the limit function comes after that are same on the former interval. Okay, then our required subsequence for which our limit function f is defined on the whole infinite interval will be the diagonal sequence. This one can also realize it easily, because when we choose the element f11, our limit function is defined on the 0 1 closed interval, and when we jump to the element f22, our limit function is defined on the 0 to 2 closed interval. When we jump to the element f33, our limit function is defined on the 0 3. So in this way, if we proceed to the infinite, our limit function is also defined on the infinite intervals. And I want to emphasize that here the fnt functions are already defined on the unbounded interval 0 infinite. Therefore, we can extract this type of sequence. Definitely here to extract the diagonal elements, maybe some selection theorem, it is called the sometimes axiom of choice is certainly used, but without the axiom of choice we cannot apply maybe the diagonal process argument also. I think the axiom of choice is hidden in this explanation. Okay, so by using this axiom of choice, we can extract this diagonal sequence for which the limit function is valid on the whole interval 0 to infinite. Therefore, most of the authors, when they apply the compactness theorem or the they do not care about the unbounded domain 0 to infinite. Instead of writing t belongs to 0 to t, they write directly 0 to infinite. But here they use a word, it is called the diagonal argument or the diagonal process. I hope that this concept is clear to you. Thank you all. Bye bye.